Okay. All right, so you guys can see that. So where did we leave off? So we left off kind of talking about this normal distribution, standard normal distribution, wanting to find probabilities of certain values being a certain number of standard deviations away from the mean. Instead, we kind of see these benchmark z values pop up a lot. They kind of correspond to 90, 95%, 97%, 1.5%, et cetera. So let's just kind of start out working through a few of these problems, kind of doing some review. So let's say I have a normally distributed variable. It's defined by two things. Its mean and its variance. So it's got a mean of 50, a variance of 100. What's the probability that if this movie theater makes 60 pounds of popcorn, they haven't made enough to meet the current demand? This is the demands distribution. So what we're thinking about is we have this normally distributed variable. This was like demand for popcorn, right? In this kind of goofy example. So we said it was normally distributed. It had a mean, which if it's a normally distributed variable, it should be symmetric around its mean. And we said the variance was 100, which would mean my standard deviation is what? Yeah, so we said it's the square root of the variance, square root of 100 gives us 10. So what we want to do, we said, okay, if they make 60 pounds of popcorn, what's the probability that they didn't make enough, or that demand is anything greater than that? So we're talking about probabilities with these distributions. If I want to know the probability it's greater than 60, that's the area under the curve to the right or above 60. So what am I going to do? I'm going to take that value of 60 and turn it into a z-score. Now, in fact, what would the z-score, if I turn the mean into a z-score, what should it always be? What is a z-score? Yeah, the number of standard deviations away from the mean. So the mean should always be 0 standard deviations away. So I know that my z-score for this value of 60 should be what? Positive or negative? Positive. So I know that the area to the right of it should be what? Greater than or less than what value? So what would be the area to the left or the right of a z-score of 0? Area under the curve is 1. So what's the area to the left and to the right of 0? So the total area is 1. What's the area to the left of 0? This is symmetric. The area is 1. It would be 0.5. They're negative z values, right? What is the probability? The probability is the area under the curve. So negative z values, the area under the curve to the left of those negative z values would be less than 0.5. If I'm thinking about a z-score of 0, the area under the curve and to the left of that, if it's a symmetric distribution, that should be half of the total area of 1, it will be 0.5. So my z-score is going to be positive. So when I look this up in the table, what's the area to the left going to be? Above what value? So looking to the area to the left here, the area to the left of 0 was 0.5. So I should know the probability of being to the left of a positive z-score would be above 0.5, which means the area to the right of it, which is what we were originally looking for, it should be less than 0.5. So if I'm thinking about these potential answers, right away, I know that it should be less than 0.5. A is not going to make any sense for me, right? So I can rule that one out right away. Now, from there, I actually have to do the work, right? What is this z-score? So we always calculate z-scores by taking the value we're interested in, subtracting the mean, dividing by the standard deviation. We're standardizing that value. So for us, that's going to be 60 minus that mean of 50 over the standard deviation of 10. Nice, easy z-score of 1. How would I interpret this? That value of 60 is 1 standard deviation above the mean. So the next step, I'm going to go to. Oh, I gotta drag this over here. I'm going to go down here to my z tables. I'm gonna look up a Z value of 1.00.8413. So that's my answer, right? What's like this? Yeah, not quite, right? Because what we were looking for was the probability of being above 60. The table always tells us this area to the left. So the table will always tell us the area to the left. If we want the area to the right, we're going to do what? Simply subtract from it. I get what? About 0.015, no, 0.1587. Any questions for any of the steps there? Okay. What if, do it this way. So we've got the answer. Here is 0.1587. If you guys haven't ever seen Mr. Nanny, also it's a great old Hogan movie. You guys are starting to get young enough to where you might not know some of these just wonderfully bad movies. But let's say we have the same setup. And I want to know what's the probability that my demand is over 60 or under 40. I actually have everything I need. I don't even need to use the tables again. So if I think about here, I've already got the probability that it's greater than 60. We know that's 0.1587. If I want to know the probability that it's less than 40, what is the Z-score? I don't even have to really do the math probably. If I look at this, what should the Z-score of 40 be? Close, 1, but negative, right? We're 1 standard deviation away, but we're 1 standard deviation below. So without looking up a Z-score of -1, why do I know the area to the left of that? Because the area to the right of a +1 Z-score, if this is a symmetric distribution, will be the exact same as the area to the left of that. So I've got 0.1587 in both tails. I would then simply add them together to get what, about 0.3 something, right? Would be that probability of seeing it be above 60 or under 40. Okay. So we can start to find kind of different ranges or different intervals, the probabilities using these Z-scores. Now the table always gives us the area to the left, and we can find the area to the right with that simple one extra step, which is just then subtracting it from 1. Okay. Any questions here before we keep moving? Hopefully we're starting to kind of remember some of this, or at least it's looking familiar, sounding somewhat familiar, right? So here's a screenshot from the movie. I kind of mentioned this last class, but you can also work in reverse. So let's say, I'll just use an example because we kind of already did this last class. I rearranged it for us. But the inverse transformation is going to say, if instead of starting with the value, I want to find the probability, I can actually know the probability I want and then find the value that would give me that. So let's say I've got a test where the mean is 72, variance is 64, and I want to know what score would put me in the top 10%. So we said last class, what am I really doing there? I'm working in reverse. I know that there is some Z-score associated with seeing 0.9 to the left, which would then give me that desired 0.1 to the right? That top 10% cutoff. So all I'm doing here is I'm working in reverse to figure out what's the X value that would give me that Z-score. Right? So I could look up in the table the probability I want, which was 0.9. So that is not going to be using the row and column headings. That's how I look up the Z value. If I want the probability of 0.9, I'm looking here. Looks like it's in between these two values. So I'll always kind of choose the higher of the two. So 1.28, 1.29, we'll use 1.29 from there. So the Z-score associated with 0.9 to the left or 0.1 to the right would be 1.29. Okay. And then from there, we've got our inverse transformation formula, which is if I want to find that cutoff X value, that's going to be take that Z-score, multiply it by the standard deviation, and then add to it whatever the mean is. So our mean was 72. I think the variance was 64, so the square root of that should be 8 if we go back to the slides. And then we have that z-score. We do this math, I don't know, what do we end up with? 8, 10.4, about 82.4. I'm going to be a little bit off there, I'm rounding, but roughly that. Now, before I do anything here, what's one way to check my work? If I know that the area to the left of a z-score of 0 is 0.5, the z-score I wanted should have been a positive value because I wanted the area of 0.9 to the left. So what should the z-score of 0, what would the x value associated with that be? Well, z-score of 0, 0 times anything is 0. It should have just been the mean, right? In which case, I know I'm looking for a value that's above the mean. Sure enough, I find something that's above the mean. Well, there's kind of these checks along the way. You can make sure you didn't like make an egregious error by thinking about the fact that the area under the curve is 1, and then you know what that means for positive versus negative z-scores, things like that. Okay. Questions on this idea? So we can work in either direction, right? So we'll go back here. We kind of work through this example. I was a little bit more precise here. I think if we plug those values in, I get 82.34. Okay. But I think I don't think hopefully too crazy here. Questions on this before I keep. All right. So the next thing we're going to talk about is hopefully we're feeling better about the standard normal distribution. We actually won't technically in Stata be using it much at all this semester. Technically, we're going to be using the student t distribution, although a lot of the times we'll use that standard normal to approximate, and I think hopefully it'll make a little more sense by the time we get to the end of today's class. So if instead I don't have the actual population data, all I have is like a sample. I only have like 50 observations. What's going to be true is if I took enough samples, so this could be, you know, a group of states, individuals, firms, a small group of countries that I don't have every single country, every single state, every single individual. We'll start notating this as not capital N for my population size, but lowercase n for my sample size. And then instead of like uppercase Y to kind of represent this population variable, we're going to be thinking, or population observation, well, with these lowercase y, here's the first observation, second observation for that variable, third, etc. All right, all the way to the very last y lowercase n observation in our data set. Okay, so it's just really just notation differences. It's basically the same thing we're doing for the population data set. It's just that our sample size, lowercase n, will be something smaller than the total population size. Okay. Now, what we're assuming when we kind of draw these samples is that any one observation, if I'm selecting randomly observations from the population, the fact that I, let's say, was choosing people at random from this class, if I select you, so given that I selected you as the first observation, it doesn't change the expected value, or it doesn't change the likelihood that I'm selecting a specific person, right? How could this be violated? A lot of times when people are trying to build samples, if I like call in for a survey and someone actually answers and will talk to me, maybe I ask if there's anybody else in the household. Well, the problem is they are likely to have correlated, if I'm, you know, even if I'm asking them questions on their political views. Well, if they live in the same household, the fact that I'm now asking the other members, they're likely to have correlated views with the person who answered the phone. So now the expected value of the political view I'm going to get is going to be different than if I was just randomly sampling from the whole population. So we can't see this violated in practice. All the examples we're going to look at, this is really just going to be an assumption we have floating behind the scenes, which is that every single observation we sample is completely random. It's not related to any other observation that ended up in our sample. Okay, so we kind of use the same similar notation. We find the mean by taking every single observation in the data set, adding up the value they have for that variable, dividing by the number of numbers we have. It's just notation differences at this point. We're not looking at the population. We're now just looking at sample data. So instead of mu, we now start writing kind of y bar as our sample mean, as opposed to mu kind of subscript y. That was our population mean. Still roughly the same. We calculate the means the exact same way. Now, regardless of our sample size, what ends up being true about the distribution. So let's say I go out, I randomly sample 50 students from my use campus. I don't know, I collect how many days, or I don't know, how many alcoholic beverages they drink a week. And then that's my 50-person data set. I go out randomly select another 50 people. I go out and select another random 50 people. If I were to look at the mean of every single one of those samples, what'll end up being true is they're all normally distributed, right? And that's because as long as that variable that I'm sampling from, or sorry, I shouldn't say they're normally distributed yet. What will be true is they'll be centered around the population mean. Because you can kind of think about it like, I've got this whole distribution. Yes, in some of my samples, I'll end up with more people that are on the right side. Sometimes I'll end up with more people on the left. But if I take enough samples, I'll end up basically sampling from every part of the overall population distribution, and my sample means will be centered all around my population mean. Okay? So we know that the expected value of our sample means will always be, or the mean of our sample means is always going to be the true population mean. We would call this then kind of our sample mean is an unbiased estimator of the population mean. Now the variance is going to depend on the size of our sample. So regardless of the size of our sample, and I think I'll be able to prove that to you here today with some data, our sample mean distribution will always be centered around the true population mean. The variance, however, how spread out that distribution is, will be dependent on how many samples or how many observations are in my samples. So think about it this way. If I'm taking samples of size 1, what could I end up with if I'm randomly sampling and looking at maybe average income? If I randomly sample people, what could I end up with an average income value of? If I selected, I don't know, Joe Rogan, right? Millions of dollars would be my average if he's the only person in my sample. Well, what happens if I still end up selecting someone who's making millions of dollars, but I've got a sample size of 1,000? Well, the other 999 people probably aren't millionaires. So when I take samples of larger sizes, it's less likely I'm going to see an average of something in the millions, right? I'm more likely to kind of get values that are closer to the mean. And so the higher the sample size I take, it's less likely I see these extreme outliers. So my distribution isn't going to be as wide, which means my variance will actually be higher or lower? Lower, right? So the higher the sample size I take, I'm less likely to get these extreme outliers that are going to influence the mean as much, because if I'm 1 out of 10 observations, I will influence the mean a lot. But if I'm 1 out of 1,000, I don't have as much influence on that sample mean. So the variance is going to go down quite a bit as we take higher samples, right? In fact, if we take higher samples, this variance of our sample means will be the variance of the original data that we're sampling from divided by the sample size. So the sample size goes up, our denominator is larger, that fraction or the variance of our sample means is going to go down. So we've got these sampling distributions. So we would kind of say this relationship says that this is a consistent estimator, okay? So I'll kind of give you kind of some data here, and then we'll kind of look at it in Stata. So I had old NBA data set that had like census of the players, and it just had player height. I was like, oh, it's an easy thing to do with height. First of all, I know that most biometric things are normally distributed, so I know I have a good example of probably something that's normally distributed. So I calculated the average height. I think it was 79.14 from the entire population. Calculated the population variance, it was 12.59. I'm then going to start to think about if I randomly sample, right? And here I had 1,000 different samples from the population data set of size 10. So I randomly would select 10 players, calculate their average height, store that in a different data set. Randomly select another 10 players, calculate the average height, store that in a data set. Continue to do that 1,000 different times. Once I had that data set now of 1,000 different sample means, we saw how easy it is to quickly find, well, what was the mean of those sample means in Stata? What was the variance of those sample means? And sure enough, what I found was to the second decimal, the mean of my sample means was almost exactly the same as the population mean. Now we'll see in practice it's going to be a little bit off, because technically for our theory to be true, how many samples would I actually need to build out the complete distribution? Theoretically, I need an infinite number of samples. So we're never going to be able to truly prove this out to ourselves with data, but we can get really close, right? And then my variance, the original variance is 12.5. If I divided that by 10, Sure enough, I found the exact same variance on my sample means as what it should have been. So we got to take a look at this in Stata. So if we go to the home page, I think what I had there was in week 2, this MBA sample distribution. So once again, kind of have Stata opened up. If we can get to this point, when I'm here, I can't save do files. I can't save anything. The only thing I can save from this interface is if I have a data set opened up, I can save data. So I actually need to open a do file. So here I kind of create a new one. This would be like where you create one for your first project or problem set, which I would start working on early. So even though I'm kicking the due date up, not to be from the end of next Thursday up to the following Tuesday, you still get working with this early because the first time doing it might take some time. So what I would generally do is kind of like I'm doing when I open this up, I will have some code that's in here. So some variable, right? And then if I ask you for the mean, well, even though that command will spit the mean out at me, I have to then kind of identify it. In your problem sets, what you should then do is kind of use this text feature. I guess technically, if you want to create a Word document where you type it all out as well, you can. It's just typing the same thing, but toggling back and forth. It seems like it'd be easier to just do it all in your do file. So mean is whatever Stata tells me, right? And then I could even set this up, make it nice and easy for Professor Lannis. I could add some, here's problem number 1. Here's problem number 2, right? You can use these kind of comments to kind of almost set it up. And that way you have your code, but you also have kind of what that code is doing or reporting the statistics that you're being asked about alongside of it. Now, the file we actually want to open up, the do file. There we go. I'll go down to my OneDrive. This is the only place I can open up files from. I can't open them up from my desktop, my downloads, only from my OneDrive. So I'm going to go to the folder that I know I've got this in. So sample distribution, right? Now, I had some people stop by my office yesterday. Another thing I would kind of suggest at this point, so I actually opened this up, excuse me, this do file up from a different folder. I have a file that I think it was you two. I explicitly told you this is what I would do. And in fact, this is what I do, right? So instead of like creating a bunch of subfolders, that's kind of sucks because then every single assignment, every single time I open something that I downloaded from Canvas and put in my OneDrive, I've got to change, okay, this is in week 3, and then this is in problem set 4 folder. Every data and do file, I would just put all in one folder so you can keep using the same file path over and over and over again the whole semester. So notice here, I've got my OneDrive, that's kind of my file path, but I have a folder that is not, I do have folders like I just opened that are broken down week by week. But what I actually have typed out into this code is one central file, one central folder where I just put everything. That way, my file path is always just this right here. I don't have to then like add in subfolders. I don't have to worry about what week or what section. Everything I use for this course, I would put in my ECON 371 files folder. Now, every time I open a do file from Canvas that I give you, or every time you want to start kind of your problem set, the files these data files you open, they're always going to be in the same file path. So here, when I put like use path, your file path will always be the same exact location, right? Wherever you're dragging and dropping these files that you're, downloading from Canvas. Now, if you want, you can always file, open, and open them up that way. But if you just want to run the code from the do files I'm giving you, that's when you would have to kind of put your own file path in there, okay? And all a file path is, if you're not clear on that, it's just like how your computer identifies like what folder these files are in, right? And this one, it's on my OneDrive under this 371 folder. So I'll set that global path. I'm going to open up this data set. In fact, might have an error because I might have moved this, right? So if I get this error, I'm like, oh man, I guess I must have my file path wrong. That's where it's helpful. The very first time you're going to identify what your file path is, go to File, Open. Now here, I'm going to go back because I want to keep using this one. So I had my 371 files. Oh, nope, that's not it. That's Econ 371. 371 files here. Make sure that I've got my MBA. what am I calling it here? NBA shots. I might have moved it. I did. So see, I actually moved my files to a different folder. So if I open up, I just saw it. Here it is, the NBA height data. Oh, okay. Something changed with the way that my cloud storage was. It actually identifies this now. Simply, this is my file path. This is the file name. This is all I need for my file path. So I can go in, I can change what that file path is. And now, if I'm using this as my global, any file that's in that ECON 371 status file on my OneDrive, it now can open that up, no problem. Now, if I go to the to the data browser with a little magnifying glass, now I can see this data file that I've opened up. Any questions on anything there? We start working with the actual data. Yeah.
Like, how'd you get that part? Like, I know, did you like import the file or like, did you like
Here?
the other part, like that stuff? Yeah, the data values.
Yeah, so you can use the code that I give to you in this NBA sample distribution file. Now the thing you'll have to change is you'll have to put whatever your file path is, wherever you actually put that NBA height data file. So that's going to be something that's on Canvas that you've got to download, then drag it from your downloads to your OneDrive, because the only place you can open things up for them is your OneDrive. But once it's on that OneDrive in whatever folder you want to open it from, as long as you get your file path correct, you can run this line of code and it'll open it up. If that's still kind of tricky for you, you can always just go to the program and say File, Open, and then find wherever you move that file. And then once you open that up, right, that's where I can now see that data set's opened up at.
So we don't need the do file thing. You don't need it if you don't have to.
You don't need it, although once we start doing things, you're going to want to have it. You want to have the do file open. You don't necessarily need this line of code to open the data file up, right? But when I start kind of running this code, you're probably going to want to work along with me or be able to kind of see what this does, you know, along with me. But yeah, that initial like opening up the data, you don't technically have to. If this file path thing is kind of tripping you up, you can always just open up that data set and then kind of start down here. Okay. Any other questions? Okay. All right, so I'm just going to keep two variables here. So I think I've shown you some of these commands before. I'm just trying to get you familiarized with some of these commands that we'll be using throughout the semester. So what this keep command does is it basically, this is a big data set. I've got a bunch of different variables. I only want to focus on two, so I don't want to scroll a bunch in this class. I just want to keep the player variable and the height variable. Right? We're focusing on this variable of height. So I'm going to hit the execute button after I highlight that line. Notice now in the data, all I'm left with are those two variables. You don't have to do this every single time. It's just, for me, it's easier than kind of worrying about scrolling back and forth. Now, if I do this, all those variables are now gone. So if I ever want to go back to the original data set, the nice thing is if I have the global path set, I can just go back to this first line, open up the original data again. All right, but once I use that keep command, the only thing that's going to be left here in my data set are those two variables. So you probably don't want to use this very often, right? I'll use it more in class. In practice, you guys probably don't want to use this. You want to keep all of the original data there. Now, I'm going to go to this summarize command. I think last class, you can use the summarize. You can also just use the sum. This is a shorthand version of it. So sum or summarize. Now, if I put comma detail, the reason why I'm doing that is because I want to look at all the summary statistics for this variable. So I'm going to execute this line of code. It shows me kind of what the percentile breakdown is. It gives me a mean of 79.14. It gives me my standard deviation, my variance, etc. Okay. Questions on this? You're having, yeah.
So I found the file, I downloaded it, and then I like opened it. But how do I open the data with like the red letters and?
Yeah, so I said the very first day of class when I introduced this, and this is where if you get lost sometimes in like opening it up, sometimes it's more important to also like listen, maybe write down some of the things I'm saying about Stata or go back to those videos and kind of rewatch the times that we're when we were talking about it. I said you usually want to have 3 windows open. You want to have this programmed open. You want to have the notepad icon or your do file open. And then you also want to look at, if you want to look at the data, there's the little magnifying glass, which is, this is going to show you the data set that you're actually working with. So it's those 3, right? That those 3 windows that you're probably going to want to be using while you're working on these. Yep. Any other questions?
What did you do with the use $ path thing? Sorry, I missed it. I was trying to.
Yeah, so all this global path does is everybody's OneDrive, you're going to be putting this file in different folders. If you want to use this line of code, I am setting it up so that it's the same. Everyone should have the same data set because I'm giving that to you on Canvas. But where it lives on your computer, your path, your file path will be different than everybody else's. So to know what that path is, this is why I said just putting it always in one folder is probably going to be easier for you. Now, the very first time you need to figure out where that file path is at, you don't have to use that line of code to open up a data set. That's just one way to make it easy to use my do files. Every single time, if you don't want to worry about that global path bullshit, you can always go to the program, you can go to File, and simply go to the interface of Open, and then just find the folder where that file is. Now, if I do that, it's a few more, I've got to click a few more things, but it'll basically do the same thing as that file path is setting the global path would, right? Now, the first time you do it, it's telling you that everything before the file that I just opened, so everything before this .dta file, this is my file path, right? That is the folder that exists on my OneDrive where I'm putting all these files for 371. Is that okay? Make a little more sense? So whatever you're seeing, if you go to the interface and open up the data set that way, whatever file path you see here before the actual file name, you would just copy. So I'm Control-C, right? Or you would copy this. And then within these parentheses, you would paste your path. Now, every single time I use this $ path, it'll open up from your computer. If you don't want to worry about that, like I said, you can always just download the data from Canvas and go to the interface and file open it yourself. Both ways will get you the same exact data set. Does that help clarify it a little bit? Any other questions? I know this is new, so these are good questions. Like I want to make sure we're getting familiarized with this before we get like too deep into the weeds, okay? And like sometimes I'll do things like this, and that's what I'm saying. Like if you don't want to mess around with this, right? Like don't mess around with the file path thing. All this is doing is just opening up the data set, which a lot of times when we have this code, there's always ways to do it from the interface. And if opening it up from the interface is easy, you can always just open up a data set from the interface. Okay? Any other questions before we keep moving? Yeah.
I'm not able to pull up the
I think so.
the thing that has all the red information.
Data?
Yeah, I go to hit the glass and
Yeah, so you have to go to File, Open,
I don't know how.
select the actual .dta data file that you want to open.
Okay.
So have you opened up that NBA 2015-16 file yet?
Okay, sorry, I was opening up the wrong.
You're okay. So I'll just try to clarify again, because I think there's some confusion. I'm guess maybe hopefully I'm saying it correctly, or I'm saying it clearly. You can only open up a do file from that do file editor that I opened with this little notepad icon. Right? So the only place, anytime you have that file that says .do, the .do file, I can only open that up from my do file editor. I cannot open up the data sets, the .dta files with my do file editor. When I'm looking at the actual program of Stata, I can open up my data files with that, right? But this is not where my do files will be. right? I will open up my do files with the do file editor. I open up my data sets using the actual program. So .dta files, I open up with my Stata program. The do file editor, that's where I open up these commands where I'm saving my commands or the .do files.
So if we wanna open set, instead of change that global path to our specific, like where we put our,
Wherever you downloaded this file to,
right.
all you have to do is change that file path to what folder you have it on your OneDrive.
If it's on OneDrive already, I know the example you said already on here, that one, like
So,
the username, library, cloud storage.
so don't try to copy what I had. So how did I say if I don't know what my file path is, what's a really easy way to first find it? I just did it for you guys.
Go to the homepage. I mean, what's in front of the .t.
So instead of worrying about this line of code, so I hear people talking and then I'm getting questions, which means I know people aren't paying attention to what I'm saying. So please listen when I'm trying to tell you, I'm trying to answer these questions, okay? So I want to make sure everyone's clear on this. I've already said it about 5 minutes ago. If I don't know how to find my file path, what is the easiest way the first time I can do that?
User interface.
Use the interface, right? Just go to the program and go to file what?
Open.
Open. Then find the data set wherever it's at on my OneDrive, right? In mine, it's in this OneDrive Econ 3. So find where you move that data set to. Open it up. It gives you, when you use that interface, it is telling you what the line of code is. So notice, this is the exact same thing. If I was going to copy this here and paste it, this is essentially the exact same thing. Now, I didn't have the clear command here because I'd already wiped out the data, so that didn't really matter. But notice, when I have this path, that is simply what comes before the file I'm trying to open. So I would use the interface first to do file open the data that way. Now you know what your file path is, and now you can simply copy and paste it into that global variable path that I'm creating so that you can run the kind of subsequent codes where it has that $ path, okay? So I know that this is a lot, and I know in class, I guess this would be my kind of advice. And I'm not trying to get frustrated, but when I'm going through it, if you're trying to do things while I'm discussing and talking to it, I'm trying to figure it out. I know it's not like you're just doing things that don't relate to the class, but I'm likely talking through something that is probably going to troubleshoot what you're currently focused on and not listening to what I'm saying. So when I'm getting questions over what I know that I mean, am I making this up? Did I not just go through this like 5 minutes ago, say this is a way to find the, yes, I'm seeing head nods. So I know that you're trying to get it work, kind of don't panic, freak out, try to focus on what I'm talking about up here and then ask your questions afterwards. You know, this is why I've been trying to stress, you know, be able to kind of open these files up, make sure you can start playing around with Stata early on, come to my office hours to ask for help getting this working, but that during class time, we're not kind of getting bogged down by some of these issues, okay? So hopefully we're getting a little more familiarized with Stata here. I know also, it's not lost on me, this is like brand new to you guys, and it's probably unlike anything you've seen in a lot of your other econ courses, right? So I understand it's probably frustrating to kind of like have almost no, I mean, this is going to be something completely new. So that's why we're trying to go kind of slow through it. I'm trying to answer as many of these questions as I can. So once we kind of get later on, we're really gonna be like going a little bit quicker through this stuff, okay? All right. So as everybody, we can get this data set open. What I really wanted to kind of get to, we need to get to by the end of the class, is talking about the sampling distribution, right? So here I've got this keep command. I'm only going to keep that height variable, okay? If I summarize the height variable, we already looked at that. It gave me my mean, my variance, etc. So I'm going to come down here. This is something, so this is where sometimes I'm trying to show you something in class. Don't feel like you have to mimic everything I'm doing here in the do file, right? Sometimes these do files I give you in class are to show you the power of what we can do in Stata, not an expectation I might have of you. So this I'm showing you what you can actually create a program that is going to go through and calculate Y bar. In the slides, I said Y bar represented my sample mean. So this is creating a sample mean. It's gonna go through, open the data set up. Now, this is why for me, it was important that I had this file path. Because I'm gonna keep reopening this data set open over and over and over again in this program. I can't have go to the interface every single time. And so I'm gonna open that data set up. I'm gonna randomly sample 10 of the observations. I'm gonna generate this additional variable, which I'm gonna call Y1, and then summarize it. And what this line of code is doing is it's storing the mean of that variable I just created. So I'm essentially taking 10 of the observations, creating a new data set where I've got now 10 players' heights, calculating the mean, and then storing that value somewhere. Okay? It's then going to go through and do this 1,000 different times. It's going to run that little program that I just created 1,000 different times. So I'm going to have 1,000 different sample means that all came from samples of size 10. Now that I have this new data set, so I'm going to run or kind of define my program and then run that program or run this simulation where I'm randomly sampling 1,000 different samples of size 10. Take a second. Here's my new data set where I should now have 1,000 different sample means. I did that very quickly. You imagine if you had to randomly sample this by hand 1,000 times, this would take forever. So I now have this data set where I've got 1,000 sample means. If I summarize that new variable, which is means, just my sample means, I said that the mean of my sample means should always be centered around whatever the true population mean was. So when we went originally, and I was looking at this data set, we said the original mean was 79.14, the variance was 12.59. So this is also nice. I can go back, rerun this line of code and always go back to earlier steps. So I now can see that mean and variance again. I'm going to rerun that program, randomly sample 1,000 different means. I'm now going to summarize those sample means. So hopefully the mean of those sample means, sure enough, it's 79.11, which is a little off of 79.14. But remember, we said it's going to be close, right? We technically would need an infinite number of samples. I only have 1,000. The variance, right? Okay, it's 1.38. Well, what should the variance of my original, where was it at? My original population data was 12.59. But we said the variance of our sample means will be the original variance divided by what? Our sample size. So if my sample size is 10, what should my new variance be? 1.259. 38. It's a little bit off, right? And this is the idea. It's because I only have 1,000, right? But it's in the neighborhood. It's close. If I wanted to take instead, what do I have one down here? So I did this. I'm not going to run this yet because I might bog down the computer, but I can do 10,000. And what I'll see is I get values that are even closer to what they actually should be. But before we get to that point, I then can create another program where it does the exact same thing. But now I'm going to randomly sample 30 individuals, create the sample. So what should happen to the variance of my sample means? If I take a higher sample size, well, if the variance of my sample means is the population variance over my sample size, when the sample size goes up, the variance of my sample means should go down. So I can actually prove that to you here as well. So the old variance was 1.38. Samples of size 30, my new variance is 0.42. Sure enough, it's lower. Now, the mean of those sample means is still really close to 79.14. Once again, it's only 1,000 off, so we're going to be a little bit off. It's going to be approximate here. But I can kind of prove these things theoretically that it should be true to myself using data. Oh, I thought I deleted that in accident. I'm going to do samples of size 100. What should be true here? Oops. In fact, I'll do samples of size 100 and I'll run this 10,000 times. We'll see how long this takes. But what should be true now is I get really, really precise kind of means of my sample mean should be really close to that population mean. We'll see it. I didn't. There we go. Sure enough, I am just barely under 79.14 and my variance here, well, it should be whatever the original 1.25 over 100 now because my sample size is now 100. Sure enough, I'm getting something that's a lot closer to that. So higher sample size, the variance of my sample means is getting even lower and lower. All right, so this is just kind of to show the power of what we can do in Stata. I mean, we just created 10,000 random samples very quickly, right? Now, this is not a do file you will need for your problem set. I won't push it this far. The one that'll be the most helpful for that problem set one will be that review of statistics do file, okay? Any questions over anything there or anything that is Stata related before we jump back into the slides? Yeah.
It's asking me if I wanted to update my Stata. And it says that I have an old version and then I use running an old version. Should I update it or not?
I using an old version?
Yeah, because it's registered, it's licensed to Indiana University and it says last updated 21st of May. However, there was
You can
one.
try to update. You might have an update on your computer. I would check that first. So that if you don't have the same system settings, mention that at being a class, like if you don't have the right, the newest one. So check to see if you have an update. But yeah, if it says that it needs to update, I would update and it probably is. I mean, you want the newest version.
Because that might be why I won't be able to save the do file.
Could be. All right, so. Where are we at here? So we kind of already talked about this. Our numbers are a little off. You know, when we use these small sample sizes, technically, we want sample sizes over 30 in order for our sample means to truly be normally distributed. So as our sample sizes get larger, we said those sample means, the mean of our sample mean starts to look closer and closer to the actual. So the central limit theorem tells us that as long as we can get a sample size over 30, not only are these things about the mean of our sample means and the variance of our sample means going to be true, any sample over size 30 should be normally distributed. Okay, so it should be that anything that has a sample size over 30, if I look at the distribution of my sample means, it should be normally distributed. So I stole this from an old textbook, but I just always kind of like this view. If I started to take from any distribution, doesn't matter if the original variable is normally distributed or not. If I sample from any distribution, notice like when my sample sizes are low, the distribution of my sample means are all kind of goofy. As I kind of get to higher sample sizes, well, some of them still have skew to them. They're not quite symmetric. But once I get to these sample sizes of 30, all my distributions will be normally distributed and symmetric around whatever that true population mean is. In fact, we could go back, I think, to kind of our, I already looked at these higher sample sizes in Stata, but I could, oh, you can't see this. We already looked at those higher sample sizes in Stata, but what we can also do in Stata is if I were to, and I'll do the smaller one just so it doesn't take as much time. If I have a sample size of 30, oh, I need my clear. When I have those sample means, what's a way we said we could look at the distribution pretty quickly? Remember the command? We had a histogram or hist, right? So that'll tell us, give me a real quick view of my distribution. So I'm gonna look at the distribution of these sample means. It creates a little image, so it might take us here a second. Okay, there's some kind of weird things going on, but right, maybe I just happen to get a couple different samples. It's pretty close to kind of a normal distribution. Now, one reason why this might not be normally distributed is guessing players of different positions have different heights. So I didn't start out with a normal distribution, which if we notice from the slides, yes, at a sample size of 30, we should approximately have a standard normal distribution here. But if we have variables that aren't normally distributed for sample sizes of 30 or smaller, we might have some things that are a little bit off, right? So it's gonna be approximately 30. Now, the higher the sample size we get. So if I looked at like sample sizes of 100, and we'll just change this to 1,000 so it runs a little bit quicker. If I instead want to look at sample sizes of 100 and look at that distribution, now it starts to look a little bit more like a normal. And if I had an even higher sample size, it would look even closer to a normal distribution, and so on and so forth. And also, this isn't a truly continuous graph, right? This is a histogram, so I'm putting things in bins. So I'm always going to have like a little bit of inconsistencies there. But anything over 30 should give me approximately a normally distributed distribution on my sample means, okay? So not only do we know something about the mean of our sample means, the variance of our sample means, we know the distribution, if we can get a sample size for 30, should be normally distributed. And I kind of already did all that work in Stata already. I kind of did it all at one time as opposed to whatever, where's the other one? Yeah, they're separating it up into 2 different points, okay? So to kind of summarize, we left off with this idea of the mean or the expected value of our sample means is the population mean, and the variance will be our population variance over our sample size, okay? So what happens if we don't know what we were taking samples. So if I was taking samples, that means I probably didn't have population data, so how am I gonna know the population variance? Well, we don't know the population variance. Excuse me, the best guess I'm gonna have is my sample variance, right? So the fact that we often don't have the population variance and to actually calculate that standard deviation of my sample means, I'm gonna have to use that sample variance that I found. When I calculate a sample variance, I don't know if I've got it here, let me see. This is kind of review going back. But if I'm finding a sample variance, how you remember from what is different about that than the population variance? So when we said we wanted the population variance, it was adding up the deviations from the mean squared over the population sample or population size. My sample variance, I'm still going to go through, I'm going to look at the difference between my sample mean and we'll use X, the different values of X. But instead of dividing by just the sample size, I actually would always be dividing by my sample size minus 1. So when I don't know the population variance and I have to use my sample variance, it's always going to be that I'm going to be off by a little bit. And in fact, how much am I, like, even if I had a sample that ended up being exactly the same as the population, my variance is always going to be a little bit what? If I subtract 1 here, that's always going to make my, like, let's say I had a sample that was the exact same size as the population.
It could be negative.
Not negative, right? So this will be a little bit what? Higher or lower? If I'm subtracting 1, a little bit lower, which means my variance is always going to be a little bit inflated, right? So I'm always going to have a sample variance maybe is a little bit inflated, even if it ended up being exactly what the population variance was. So how much inflated is it? Well, if this was 2, dividing by 1 instead of 2 is a big deal. Dividing by 100 instead of 101 wouldn't cause as much of a difference. So the higher the sample size we have, the less this is going to be an issue. But we want to take it into consideration that when we're calculating, if all we have is the sample variance, the fact that in our denominator is n-1, we need to account for this. So we come up with something called degrees of freedom. Oh, I didn't hit the one screen. There we go. So all my degrees of freedom is going to be my sample size minus 1. It's going to tell me how much it matters that I'm subtracting by 1 to calculate the sample variance. So what's going to happen is instead of having a normally distributed variable, when I create a z-score, I'm subtracting the population mean and I'm dividing by the population standard deviation. If all I have is the sample standard deviation, when I standardize these variables, try to create z-scores, they won't actually be coming from that standard normal distribution. They won't be z-scores. Every single different sample size has its own distribution. We call this set of distributions our student t distributions, okay? So they are, like the standard normal, going to be symmetric. So they look like they have the same exact shape, right? They're this nice bell curve, right? They're centered around 0. And the mean will be equal to the median. Now, they're gonna be a little bit more spread out. So this was the idea that we said when we're doing n-1, our variances are always gonna be a little bit higher, right? We're always gonna have a little bit more spread to these distributions. Now, once we get to a degrees of freedom of 100, the student t and standard normal are basically the same. They're so similar that to the second or third decimal, they're unidentifiable, right? They're any different. So what are they gonna look like? So let's say I've got my standard normal distribution. If I had a degrees of freedom of 20, so what would my sample size be here? Degrees of freedom is n-1, my sample size would be 21. So notice it's gonna be a little bit flatter of a distribution, or the tails have higher probabilities, meaning it's more spread out, right? The variance, if it's more spread out, is higher for the student t distribution. Now, if I take a higher sample size or my degrees of freedom goes up, what's that gonna do to my variance? So if I've got n-1, if n is going up, my denominator is larger, my variance is going down, which means my distribution is gonna be less spread out or more kind of peaked. So if I'm going from a smaller sample size to a higher sample size, my distribution is becoming more peaked, that variance is getting smaller, and it's gonna get closer and closer, right? As that variance gets lower and lower, it's gonna get closer and closer to that standard normal distribution. Now, I'll draw this out for us, but just to kind of check what we're thinking about here, what was the variance of our standard normal distribution? So these z values had a mean of 0 and a variance of 1. So our student t distributions, they have a mean of 0, but if the variance is higher, all of them will have a variance that's what? So we said the standard normal distribution is like here. And then our student t distributions we knew were going to be like squished down. So if their variance is higher,
More than 1.
has to be greater than 1. Right? Now, I'm not perfect at drawing these, but this really drawing these exaggerated. So here was my kind of standard normal or my z values. And then here's kind of just a student t distribution, right? For some degrees of freedom. Notice if I was looking at my standard normal and I wanted to think about, okay, if I had a z score, so if we're plotting these on the same graph of, I think 1.96, that should, if I looked that up in the z table, if I remember right, that should give me 0.025 to the right of that value. Well, notice if my student t distribution is more spread out, if I keep using that same z value, what's the probability from that student t distribution I see something 1.96 standard deviations above the mean or anything greater? That probability is going to be what? Yeah, greater than 0.025. So I can't keep using these same cutoff values that I was using for my standard normal for these student t because they're a little bit more spread out. Those probabilities won't be the same. In fact, if I want 0.025 in that tail, what's going to be true about the student t value that I need? Yep, it needs to be somewhere out here, right? Greater. We don't know exactly where without using the table. Now, instead of making you use the tables, right, for these student t, which I kind of am going to show it to you here, and I put the PDF up there. In practice, we won't really be using these by hand a lot. Ultimately, once we get to confidence intervals and hypothesis testing, we're going to be using the same kind of benchmark values, and I'm not as focused with you using the student t distribution tables, other than just knowing what the differences between that student t distribution is from the standard normal. So you'll notice here, if I want 0.025 in the tail, well, notice that when I've got degrees of freedom or sample sizes that start to get relatively large, what is this getting closer to? That standard normal value. In fact, if I can get to an infinite sample size, which we can't, but in theory, if I could, I'd be using the exact same values as my standard normal, right? So our student t values will always be, to get the same desired probability in the tail, will always be larger, right? I want the same probability or the same area in that tail. The t-value I need to use will always be greater than that z-value, okay? And that's because it's more spread out, okay? And so another nice thing about the student t-tables is the very last row. Instead of like hunting down 0.9 or 0.02, whatever it is, the last row actually gives us the standard normal values. And we'll end up using like the same benchmark cutoffs, like 0.1 is like the 90th percentile. 0.05 is like the 95th. So this last row of our student t-table is going to show us basically what those standard normal values would be, right? So it's kind of nice. It's almost like we're concerned with are these benchmark values. It's already kind of baked into the same table for us, okay? All right. I'm at 26, okay. All right, so what do I want to say here? So we've got hypothesis testing is kind of the next thing that we'll look at. So I probably took a little more time in this data than I wanted to today. But I do want to set us up for next class, kind of thinking about hypothesis testing. We've got 10 minutes. I'll at least introduce this idea so that we kind of have a way to kind of dive off of. So hopefully, does this term ring a bell for you guys from 370? So when we're doing this hypothesis testing, what we're really saying is we have three different types of tests. We're going to call them right, left, and two-tailed tests. So what we're going to do is say, okay, look, we want to know, is the true population mean? So we're going to have this H subscript 0. This is what we're going to assume to be true. Okay. So I'm going to assume, this is going to be our null hypothesis, that the true population mean is less than or equal to some value. So mu subscript 0 is just this value that we want to test to see is the true mean above or below this value. We will kind of assume that it's less than or equal to this value. Whenever our alternative test is, our hypothesis test is, we want to test for whether or not it's above that value. So whatever I want to try to find, I'm always going to stack the deck against myself. So if I want to know is the true population mean above a specific value, I assume it's less than or equal to that. And then I go out and collect data and see, can I find evidence that goes against that null hypothesis enough that I can reject it? If I want to know, is the true population mean less than a certain value? I assume the opposite is true, that it's greater than or equal to that value. I go out and try to find data to see if it goes against that enough where I can reject it. I might just want to know, is it different than a specific value? Right? I don't care what direction, what side, or what side of the value it's on. I just want to know, is it different than this specific value? I go out, collect data. If it supports the null enough, if it goes against the null enough, I would then reject it. Okay. So we'll kind of call these our one and two sided, right? These one-tailed tests where only one side matters. Two-tailed tests is where I don't care what direction it's, what side of the mean it's on. I just care is it anything different than the mean. Okay. So what we're going to do for basically all this class is we're going to come up with these test statistics, right? To do the hypothesis testing. All the test statistic is it's going to look very similar to when we standardize a variable. So I'm going to create this t-value. Right? So where does this come from? We'll write this out and we'll kind of here. When we were standardizing a variable, we subtracted the mean divided by the standard deviation. When I'm turning a sample mean into a t-value, the t-value will still, you can kind of think about it as somewhat still representing the number of standard deviations away from the mean. So we're going to subtract whatever the mean is, but here we don't know the actual mean. So we're going to take the sample mean that we found and we're going to subtract that assumed true mean, right? That's the value that we're actually testing against or testing for. So if I divide by the standard deviation of my sample means, well, what was the equation we had for the standard deviation of our sample means? Well, our sample variance of our, the sample variance of our sample means would have been like that sample variance over our sample size. We want the standard deviation, so we take the square root, right? So that's kind of where that comes from, right? it's really kind of very similar to this idea that we're trying to standardize this sample mean value we had. So we're really doing the same thing. We're subtracting the mean of this statistic. So the mean of our sample means should be the true population mean. We don't know the true population mean, but we've assumed it's a certain value. We then would divide by the standard deviation of that statistic. The standard deviation of our sample means will be whatever that sample variance, the best guess we have of what the population variance is, over our sample size, and then we take the square root. Okay. Questions on this? So we come up with these test statistics. We're going to start thinking about rejection regions. Does the test statistic fall in these rejection regions? We'll kind of pick up with this next class. I did want to, before we get out of here, I had it sitting here. Yeah. And I just want to make it available. So this one's not going to be for any points. And in fact, I'll probably just kind of gloss over it here quickly because we only have a couple minutes. But as long as I have these created, I figure I'll share them with you. So even though there's going to be class periods where I don't necessarily use these in-class quizzes for points, I'm going to try to kind of generate some questions that go along with every lecture, even if we're not kind of using them. So I said there's only going to be 12 throughout the semester. These two are just additional questions you can kind of think about. I'll start to kind of use these practice questions in classes and just present them to you as well. So we're thinking about the student t-distribution compared to our standard normal. Which of the following is going to be true? We haven't gotten to these critical values. We haven't gotten to p-values, so we're a little bit, we didn't quite get here yet. So after Tuesday's class, we'll probably revisit these. I'll have a different set of questions that I'll probably use next week for actual points for an in-class kind of participation quiz. But I want to kind of put these questions up. You can start to think about as we go through Tuesday's class, how we can hopefully answer these at the end of Tuesday's class, which is basically, how do I make rejection decisions using the critical value p-value approach for hypothesis testing? We'll then start talking about confidence intervals, finish up confidence intervals, which should be kind of the last real thing we need for both that quiz and the first problem set. We should kind of have everything we need after Tuesday's class for both of those. Like I said, I'll change the due date on that problem set so that it's a little bit, it's bumped it up one class period since we didn't quite cover everything today. And we won't have that first quiz until after Tuesday's class next week. Okay. So I can't stress enough, try to make sure you have stayed working on your device. If you don't, office hours Monday, I likely will have to only do them via Zoom. But if you want to meet and kind of go through and kind of help you troubleshoot, shouldn't be a problem to have to do that by Zoom. If you don't have it figured out by Monday, please reach out to me. Set up a time that we can kind of talk on Monday where I can help you make sure you're getting state of work on your device. But that should be the last possible point where it's okay. Other than that, have a fun, safe weekend, and I will see you guys on Tuesday.
I have a question.
Yeah, one second.